Swayam Prabha. Digital India. Educated India.
Previous lectures we have been dealing with one kind of common fault in rotating machinery, that is unbalance. Apart from this unbalance, there are several other faults which may appear in rotating machinery, and those obviously reflect in the vibration signature, because whatever the dynamics is taking place inside the machine, that reflects as a vibration, and if we measure the vibration onto the machine body or any other component, then we can able to have some idea about the condition of the that particular machine component. So, in the today's lecture we will be dealing with various kind of common fault in the rotating machinery and how it affects the vibration signature, and we will try to analyze these vibration signatures. Are there in time domain, generally we captured through some sensor, and then we are generally these whatever the signal comes in analog form, then we convert into the digital form using analog to digital converter, so that we can able to store the data in computer, and then we can able to do the post processing of those data. Either we can convert the time domain data into frequency domain or any other domain in which these signals can be interpreted. So, we will start the introduction to this particular topic. So, it is very important to display the measured signal in convenient form, so as to be useful for the interpretation of the condition of the rotating machinery. As I mentioned, the measured signal we need to display in a convenient form, which will be useful for the finding the condition of the rotating machinery. As we will go into the deep into the lecture, we will find how these signals can give condition of rotating machinery. So, looking at various forms of measured signal, possible condition of machine is provided. It also looks into the correlation of a particular signature or the vibration signature with a particular failure in more detail. Every fault has a specific signature in the measured signal, and it is most convenient and cheapest way to identify possible fault in machinery. Now, very advanced signal processing techniques like wavelet transform, neural network, fuzzy logic, genetic algorithm, genetic programming, machine support factor SVM are being applied in vibration signals of laboratory test setup to detect, locate and quantify the faults. So, not only the detection of the fault, now with these techniques we can able to pinpoint where is the fault, and even we can able to quantify the fault, and based on this even the life of the machinery is also being predicted, how much we can able to run the machine without much danger. So, detailed treatment of these newly emerging methods is beyond the scope of the present lecture, but mainly we will be focusing on based on signature, based on the vibration signature, we will try to correlate various kind of faults in the present lecture. So, vibration based identification of fault such as rotor unbalance, rotor bends, cracks, rubs, misalignment, fluid induced instability, based on the qualitative understanding of measured data is well developed and widely used in practice. So, even this is being applied in actual machinery in industry also. However, the quantitative part, the estimation of the event of fault or the extent of the fault and their location has been an active research for many years. So, qualitative we can able to detect the fault, but quantifying that is still a research area. Over the past 3 to 4 decades, theoretical models have played an increasing role in the rapid resolution of problems in rotating machinery. So, the most common fault which we already seen is the unbalance. So, let us see slightly more detail on this. So, in any rotating machinery, the rotor unbalance is always present, and it is one of the most common source of severe vibration in rotating machinery. When a severely unbalanced rotor is rotated freely on frictionless bearing, it stops at nearly fixed orientation. So, this is nothing but the static balancing of the rotor. It indicates that the gravity force acting at the center of the gravity pulls the rotor to a fixed orientation due to its eccentricity. So, this we already discussed regarding the static balancing of a practical rotor, how we can able to do it. So, there are two terminology. One is the position of the unbalance, that is we call it as heavy or hot spot. This position is always remain fixed onto the shaft. The point on an unbalanced rotating shaft with the maximum displacement is called the high spot. So, that is heavy spot, and high spot is the where the maximum displacement of the rotor take place in the axial position of the rotor, and this point is variable and depends upon the speed of rotor, and it is observed by vibration pickup or sensor as a point of maximum positive displacement or amplitude of vibration. And because once we are rotating the rotor in the flexible mode, we know that this high spot may change. So, that is why it is depend upon the this particular speed. So, this is a typical unbalanced response. This is the you can able to see there are two critical speeds of the rotor. This is the phase plot. So, phase is also changing wherever there is a peak. So, this is another way of identifying where are the critical speed. This is the orbit of the shaft, that means in vertical direction and horizontal direction displacement can be plotted like this, and we can able to see even in some instruments we can able to see the sense of rotation of the this particular orbit using a z direction. Even in some oscilloscope we can able to see this particular orbit, the sense of rotation also, and using a third axis. So, x and y, and another axis that is z axis. In that we can able to introduce a reference signal, and with the help of that we can able to show the sense of the this orbit also. So, this is below the critical speed, but so critical speeds are there, you can able to see at so 200 rpm is below the first critical speed. So, sense of rotation is in this particular case counterclockwise direction, but if we are between two critical speed, the sense of rotation is changed, or it is clockwise, and if we cross the second critical speed, again it rotates in the counterclockwise direction. So, this also indicates how in which region of the critical speed range we are there. Even the shape of the orbit helps us in understanding the especially what kind of fault may come into the rotating machinery. So, as we will see in the subsequent slides, that the shape also gives indication of incipient fault in the rotating machinery. So, the high and heavy spots may or may not coincide depending upon whether the rotor is operating relative to the critical speed. So, in a Jeffcott rotor, the example which I showed in the previous slide, it is observed that the high and heavy spot coincide below the critical speed, and they are opposite above the critical speed. At critical speed, they have a 90-degree phase with heavy spot. These kind of phase we already seen in very beginning of these lectures when we considered the Jepcot rotor. In some instances, the magnitude and the phase of the unbalanced vibration vector might change with time. When symptom of unbalance exhibit this feature, the correct treatment is not normally to simply rebalance the machine. So, if magnitude and phase of the unbalanced vibration is changing with time, then there is not a balancing problem, that is a different problem. The example of fault in such category are the heavy spot on the shaft causing a thermal bow. It occurs when the heavy rotors of turbine are left non-rotated for cooling during shutdown, and due to heavy sag it get permanent bent configuration, or even when the rotor has axial asymmetry of the thermal distortion. So, because of this we may find that the response may change over period of time. Components mounted loosely on shaft like discs, gear, flywheel, etc. If that is the case, then also we find this particular kind of behavior in the response. Moisture entering in a hollow shaft, which vary in amount and location during the operation of the machinery. So, this is another potential cause of that we may find that the response may change over time. Now, coming to the unbalance, we have already seen how the procedure how to balance a rotor. So, this is a typical rotor in which there is a motor, the bearings are there here, this is a fluid film bearing and this is a Bush bearing, this is a 2 discs and is mounted on flexible shaft. There are provision to measure the vibrations at several locations. So, we can able to use proximity displacement probes to measure the displacement. So, you can able to see this is the shaft, these are the proximity probes. So, there is a gap between the shaft and the probe, and when gap changes it produces the current proportional to that, and we can able to measure the displacement. And this is a fluid film bearing in which we can able to measure the pressure also at various locations. And this is a disc, and you can in this particular disc you can able to see there are threaded holes in which we can able to put some kind of screw, so that we can put some kind of trial mass in this. So, basically we can call this as a perturbator disc. Now, this is a typical response. So, this is without unbalance. So, you can able to see this is a response of the rotor. This has been filtered at the rotational speed of the rotor, that is why it is so perfectly sinusoidal in nature. This is a reference signal which we generally keep at keyway onto the shaft, or by putting some kind of tape, photo reflecting tape. So, these spikes helps us in finding the phase of this with respect to this reference signal. So, it has been balanced by the procedure described earlier, and now you can able to see after putting the correction mass, again we measured the displacement, and you can able to see compare there is a drastic decrease in the amplitude of the vibration took place after balancing. Next category of the fault is the shaft bow or thermal bow, as we have seen in the previous discussion. These bows in shafts may caused in several ways. For example, due to creep, thermal distortion, or a previously large unbalanced force. The forcing caused by a shaft bow is similar or slightly different to that caused by conventional mass unbalance. The bow and the eccentricity are in general in different angular location, and warped rotor behave somewhat differently from purely unbalanced rotor. So, unbalanced and the bent rotor, they have slightly different behavior. Bowed shaft response is independent of the shaft speed. This is very important to observe. This particular thing is independent of the speed of the shaft and causes different amplitude and phase angle relationship than is found with the ordinary mass unbalance, where the forcing is proportional to the square of the speed, because we know for unbalance the force is proportional to the square of the speed, but for the bowed shaft it is not the case. Both shaft gives rise to synchronous excitation as with the as the mass unbalance, and the relative phase between the bent and the unbalance causes different changes of phase angle through resonance than would be seen in the pure unbalanced case. So, this is a typical a test rig in which the bearing blocks are there and there is a shaft, and we can able to introduce a bow in this particular shaft. That means permanent bent we can able to introduce, and we can able to rotate this shaft by some motor, and then we can able to measure the vibrations at some location onto the shaft. And this is a particular these vibration have been measured at the bearing block through accelerometer. So, now you can able to see in this, basically this is a horizontal and vertical response. This is in the frequency domain from 0 to 200 hertz is the frequency span in this, and this is the amplitude of vibration. This is in horizontal and this is in the vertical direction, and this is without any bow into the shaft. At one particular speed 1000 rpm it has been rotated. Now, you can able to see this is corresponding to the 1x, that is corresponding to the rotating speed of the shaft. This is also corresponding to the rotating speed of the shaft. Speed is 1000 rpm, which is relatively low, and this is the response when we introduce the bend into the shaft, and we are measuring the vibration from the bearing housing. At the same speed we are operating as this one, and in this we can able to see there is still those peaks are there, but the amplitudes are different. You can able to see here is 9.2, but is 15.0. So, amplitudes are different, and but not much appreciable amount of difference was found between these two responses for slow speed of operation. So, this I discussed. This is the same experiment with slightly higher speed at 5000 rpm. This has been taken from SpectraQuest case studies. In this you can able to see that this is the corresponding to the rotational speed of the shaft. This is in the horizontal direction, vertical direction. This is a baseline, that means without bend, and this is with bend. And with bend we can able to see there is a change in the amplitude of vibration. Now, quite drastic change in the amplitude of vibration of at the rotational speed frequency we observed. So, in this a careful inspection of the previous two figures indicate that the amplitude 1x, that is rotational speed, has a significant increase both in the horizontal and vertical directions. They increase 3 to 4 times respectively. The experimental results indicate that for low speed the effect of bent shaft on bearing vibration can be neglected. Under high speed 5000 rpm, a center bent shaft, the bent was there at the center of the shaft, will increase 1x of the bearing vibration. So, we are measuring the vibration at bearing. So, it has been observed in the previous figures that for high speed the bent shaft is having significant effect onto the 1x component of the vibration. Next fault is the misalignment. Unbalance and misalignment are the two most common source of vibration in the machinery. Objective of the alignment is to have two coupled shaft perfectly collinear under operating condition, or between the bearing and the shaft their axis should be collinear, or the two bearing carrying a common shaft should have their axis collinear. So, these are the condition is the perfect alignment, but if it deviates then we will be having misalignment in the system, in the rotating components. So, accordingly misalignment can be classified as parallel, angular, or combination of parallel and angular misalignments. So, this we can able to see here. There are two shafts, rigid shafts, and they are offset by some amount. So, this is parallel this shaft axes are parallel, but they are offset. So, this is a parallel misalignment. Then another is in which two shafts are having some inclination. So, this is a angular misalignment, but there is no parallel offset. And third is the combination of both parallel as well as angular. So, in this both the parallel and angular misalignments are present. So, we can able to expect that there will be large forces which will be coming out of the bearing because of this misalignment, and that will reflect in the vibration signatures. Like the unbalance, the misalignment is an installation, and again I am repeating this. Like the unbalance, the misalignment is an installation and subsequent maintenance problem, since it can be corrected and prevented by using the proper installation and maintenance procedures. The vibration associated with misalignment occur at one machine running speed, but unlike unbalanced case, there is a usually substantial component in the axial direction, which may be greater than the radial direction. So, apart from the radial vibration, we can have axial vibration in this particular case when the misalignment is present, which is not there in the case of unbalance. In unbalance, only pure radial vibrations will take place. Substantial amount of misalignment or the preload can also cause vibrations at frequencies of two machine running frequency, twice of the machine running speed, and sometimes higher multiples also, 3, 4 also. So, this is a typical cascade plot with shaft misalignment. So, this is the vibration frequency, this is the shaft running frequency. So, you can able to see this is the 1x. So, amplitudes are present in this. Even in 2x machine, some of the peaks are present as we are increasing the speed. 3x few are there. So, this kind of behavior we can able to get when the misalignment is present in the system. So, this is the Lissajous plot for different level of misalignment. For moderate misalignment, we will be having elliptical shape of the orbit or the Lissajous plot, which is nothing but the x and y plot as we have shown earlier. But for heavier misalignment, we have banana shape, or for very severe misalignment, we will be having shape of 8 or maybe multiple loops we may find because of severe misalignment. So, by looking into the these plots, we can able to pinpoint that whether the rotor system is having some kind of misalignment, and what is the degree of misalignment we can able to identify with this. Now, we will take up one case study, which is of a stone crusher unit in a cement plant. So, in this this is a typical industrial stone crusher. Basically, here motor is there, drive is there, then this is the coupling unit which we can able to see it, and then in this side there was one crusher unit in which the stones used to crush from bigger size to smaller size, and in this particular case they had a lot of problem of the vibration. Basically, this whole unit was mounted on a platform, and if we basically it was in the first floor kind of thing. So, if we see from bottom, so this was the support to mount that machinery at the top, and they had a lot of vibration in this. Order of vibration was very large, and because of that even in the columns, so whatever the this kind of columns, they had the cracks in the columns, and the machine was in a very bad condition, and they were not knowing what is the actual cause of such vibration. So, we took measurement of that particular vibration, and then after 1 week of that there was total shutdown of the plant, and this is the typical gearbox they took out and try to find out where is the failure of the machine took place. So, basically at the rear end of this gearbox, this is a spline shaft which connects the this particular gearbox to the store rollers. So, this spline shaft is shown here in more close view of that. So, that spline shaft has had crack, and this is the crack which is very severe crack is present in this, and this was after the measurement we took. So, that was after 1 week this happened, and this is a typical vibration measurement which we took prior to the failure. In this we could able to find out some of the frequencies which were natural frequency of the system, because in several plots they were appearing and disappearing. So, whenever there was excitation close to this, they were appearing, and otherwise it was not appearing. The gear mesh frequency, one of them was here. This was a typical low frequency peak which was otherwise should not have been present, and we found this was because of the misalignment between the spline shaft and the roller shaft, and that misalignment when we calculated because the speed of that was very low, and this is the typical misalignment behavior we could able to identify from this vibration signature. So, this is a typical case study on the misalignment, how we can able to find out through vibration signature directly. Next kind of fault is the stator rotor rubs. So, when the rotor touches the stator, there will be rub, and this may reflect in the vibration signal. So, rubs are produced when the rotating shafts comes into contact with the stationary component of the machine. Rubs are said to accompanied by a great deal of high frequency spectral activity. A rub is generally transient behavior is there. The rub may typically be caused by the mass unbalance, heavy mass unbalance, turbine or compression blade failure, defective bearing or seal, or the rotor misalignment, either thermal or mechanical. Several different physical events may occur during a period of contact between the rotor and the stator. The initial impending stage, frictional behavior between the two contacting parts, an increase in the stiffness of the rotating system while contact is maintained. The behavior of the system during this period is highly nonlinear and may be chaotic also in the nature. Some of the research have been reported that this may give a chaotic behavior of the system. The rotor to stator rub is one of the malfunctions occurring often in rotating machinery. It is usually a secondary phenomena resulting from other faults. So, because of the other fault this comes, that is why it is a secondary phenomena. Rubs may be classified as a partial rub, full rub, or take a form of a stick slip action. A partial rub is that where contact between the shaft and the stationary component exists only for a part of the cycle. For example, the high spot on the shaft rubs against part of the seal, or a bowed rotor rubs the stator. The flattened waveform and orbit are strong indication of the partial rub. So, from the waveform we can able to identify whether rub is taking place if it is getting flattened. In the case of full rub, the shaft may make contact with stationary member not only at local high spot, but instead bounce its way all around its orbit. For example, in case of severe misalignment or due to severe unbalance which produces large unbalance response in the rotor. The main component is at 1x rotational speed. Harmonics and subharmonics may also be present in either the forward or backward directions because of the rub, full rub. This is a typical plot of the vibration which take place due to the rub. So, this is without rub, and with rub you can able to see various higher order components have appeared. So, this could be the indication of the rub in the rotor system. Mechanical looseness of component, this is another kind of fault which is which comes into the system because of the poor maintenance. So, mechanical looseness, the improper fitting between component parts is generally characterized by a long string of harmonics of running frequency with abnormally high amplitudes. In some machines, vibration levels may be excessive as a consequence of component being assembled too loosely. For example, in the case of bearing which is not properly secured, the vibration signal detected from a transducer is normally a sine wave, but is truncated at one extreme as shown in the figure. So, that means vibration signal should be sinusoidal, but sometimes we will see that at one extreme is getting flattened, and because of this looseness. So, a truncation of sine wave occurs because of non-unity of, for example, the bearing mount that suddenly becomes very stiff when the loose component reaches the limit of its allowable level. The frequency domain, in frequency domain, these truncation impulses show up as a series of harmonics of rotational frequency. So, if we see this particular signal in frequency domain, there will be a fundamental harmonics and then higher harmonics will be there. For this intact without looseness, we expect only single peak, but because of the truncation, now we will be having multiple harmonics of the signal will be present. Next common fault in the shaft, especially for where the high power transmission is there, there is a shaft cracks. The presence of various flaws such as cracks, notches, slits, etc. in any structure and machinery may lead to catastrophic failures. They are particularly likely to occur in instances where shaft stresses are high and where machines have endured many operation cycles throughout its life, so that material failure has occurred as a consequence of fatigue. In the shaft cracks, again I am repeating, if the shaft cracks can be detected before catastrophic failure occur, then the machine can be temporarily taken out of service and repaired before the situation gets out of hand. The presence of transverse shaft crack sometimes detected by monitoring change in the vibration characteristics of the machine. The shaft stiffness at the location of the crack is reduced by an amount depending upon the crack size. That is in turn affects the machine natural frequency, so that changes in the natural frequency may be could be a symptom of the shaft crack, because crack introduces flexibility in the shaft that changes the stiffness, and natural frequency is nothing but root k by m. So, if stiffness changes, we expect there will be change in the natural frequency of the system. So, that could be one indication of the crack in the rotor system, but unfortunately the changes in natural frequency may not occur until the crack has reached a dangerously large size. For this reason, most user for rotating machinery depend on changes in vibration amplitude, phase and frequency spectrum to detect shaft cracks rather than the change in natural frequency. A transverse crack or the breathing crack, sometimes we call it, in which continuously opening and closing of the crack take place during vibration, that results in significant change in both 1x and 2x vibration component. So, not only 1x and 2x component are also present in this. So, as I have shown earlier, this is a typical cracked shaft, but we measured the vibration at the housing of these, so that we could not able to locate this particular behavior in the vibration, but if we could have taken near to this shaft, we could have got some indication of the cracking in the shaft. Till now we have seen some of the very common fault in the rotating machinery. There are various components in the rotating machinery which do get failures, and they have special frequency components like bearings and gears. So, now we will take up a case of bearing faults, because in bearing we know there are various components and any of the component can fail. So, for rolling element bearing fault, the primary example of characteristic associated with a specific component is the frequencies generated by the defects and flaw in the rolling element bearings. Faults in rolling element bearing may occur prematurely as a consequence of operating the bearing under appropriate loading condition, inappropriate loading condition, including misalignment and excessive speeds. Alternately, they may be produced simply as part of normal wear process during the life cycle of the bearing. Defects in the bearing may be developed on either raceway, on the rolling element or themselves, or on the cage. Subsequent vibrations are forced as a consequence of impact between the fault and the bearing components, so that the frequency of the resulting vibration is largely dependent on the frequency of impacting. For example, a defect in a bearing outer raceway would set up vibrations corresponding to the frequency with which rolling element passed over the defects. Consideration of bearing kinematics geometry enables calculation of these frequency associated with defects in different component of the bearing. So, if we see the bearing, this is a deep groove ball bearing. So, you can able to see this is a rolling element, outer raceway, inner raceway, and we can have fault in any of these two, four components. This is the contact angle. This is the mean diameter of the bearing. This is a ball diameter. So, based on geometry, we can able to calculate the outer raceway defect frequency like this, where Z is the number of rolling element, N is the speed of the shaft, and these I have already defined. Similarly, inner race defect frequency can be given by this, rolling element defect frequency, cage defect frequency. So, these frequency we can look into the vibration signal if we are monitoring a bearing. So, even additionally, sum and difference frequencies may be apparent as a result of interaction or modulation between two or more characteristic frequencies. So, even with the rotor speed and the other defect frequency, there can be sum and difference of the frequency may be present in the spectra because of the modulation. Such sum and difference frequency appear as a side bands of frequency peaks either side of the higher main frequency component of the signal. So, side bands are nothing but frequency, there will be predominant peak and either side of that there will be two smaller peaks. So, that is called side bands. For example, let the carrier or the central frequency is omega c, the carrier signal is sin omega t, and the modulation frequency would be, let us say, omega m, and the modulation signal is some constant plus sin omega m t. Then multiplication of this can be written like this, and the sin omega c t and sin omega m t can be again rewritten like this. So, you can able to see that basically we are getting the sum and the difference of the frequencies. So, in general, side band frequency could be central frequency plus minus of the n times the modulated frequency. Some of the plots will be showing in the subsequent slides. A wear of the bearing progresses, as the wear of the bearing progresses, the frequency spectrum changes further. Sometimes higher order harmonics of the defect frequency becomes present, sometimes with their own sidebands and can dominate the spectrum. So, even the high frequency component can be there in the bearing fault. The micro irregularity of the bearing contacting surface give very high frequency component in the response. A popular method of monitoring rolling element bearing condition is the shock impulse method. The basic principle of this is the method depends upon the signal input to the measuring instrument like accelerometer being passed through a narrow band filter whose central frequency is corresponding to the accelerometer natural frequency. So, basically as the part of the bearing collides with the defect, a shock wave is transmitted through the bearing and the machine casing, thus exciting the accelerometer by means of a pulse input. And because the frequency is close to the accelerometer natural frequency, so we will get a very high amplitude of vibration. So, this is one case study for the bearing. So, the physics and the physics sorry. So, based on the geometry and the calculated frequency for the one of the machine fault simulator we have taken, in which the bearing was of this category and various parameters like number of rolling element, ball diameter, pitch diameter, contact angles are given here. And based on this specification, so these are the specification of the bearing, and these are various frequency factors which we have obtained from the previous formula. So, only thing, the speed is not there in this. So, whatever the formula we given, so if we remove the speed part and by 60, these are the factor are there. So, you can able to see FTF is the thing, but the cage defect frequency, BSF is ball defect frequency. Similarly, this is ball passing frequency for outer raceway and this for inner raceway. So, this is for outer raceway defect, this for inner raceway defect. So, these are the factors. So, if we multiply by the speed of the rotor, we will get what frequency will be coming because of these faults. So, at 10 hertz, if we are operating the rotor, so we can able to see different kind of fault. These are the factors. So, we will be having the frequencies like this corresponding to the various faults, inner raceway, outer raceway, like that. Similarly, for 20 hertz we can able to calculate. So, basically the main purpose of this to find out where we should look into the signal, these frequencies. So, these are the various frequency, these are the closest value corresponding to the calculated frequency of the faults. So, this is a typical signal in which the inner raceway defect is there. So, you can able to see that there is. So, in this experiment we had normal bearing and bearing with various kind of defects. So, we measured the signal with normal bearing and with various defects, and we plotted in the frequency domain. So, this particular peak you can able to see is corresponding to the inner race fault frequency, and which is very close to the calculated ones. Similarly, this is for the outer raceway ball, outer raceway fault frequency, and so this is very predominant, and the value which we calculated earlier is close to this, and based on the speed of the rotor they may change as we have seen in the previous calculation. Similarly, this is for the rolling element fault at 10 hertz. So, some spike we can able to see. So, if we have baseline signal in which there is no fault, and if suddenly such peak comes, then we can able to pinpoint what kind of fault is there in the bearing. So, this is when combined fault is there. So, you can able to see outer raceway, inner raceway, and all kind of faults, ball fault is there. All we can able to see when simultaneously all faults are there in the bearing. So, that will reflect in the vibration signal, all the frequencies. Now, we will take up another machine element, that is gear, in which we can have several kind of fault. So, one typical case study will be taking up after a brief description of the gears, in which what kind of frequency it can produce in the vibration signal. So, the forces in the fault in the gear, the forces generated at gears are finally transmitted through the bearing to the base of or the foundation. Thus, vibration measurement taken at the bearing can also indicate the condition of the gearbox. So, finally, whatever the dynamics is taking place at the gear will reflect at the bearing location, and if you are measuring the vibration there, it will give the condition of the gear also. So, gears typically generate a complex broad vibration spectrum beginning with frequencies well below the shaft rotational speed and extending to the several multiples of the gear mesh frequency. Gear mesh frequency is nothing but the number of gear teeth times the shaft speed. So, the amplitude of mesh frequency may vary greatly from gear to gear depending upon the number of teeth, gear ratio, or tooth surface finish and load. As a general rule, the amplitude of mesh frequency will be smaller with a larger number of teeth, lower gear ratio, high quality of gear finish and lower load applied to the gear. A narrow band spectrum analyzer is very useful for this purpose, because the monitoring processes involve the detection of discrete frequency component that must be distinguished from frequencies generated through other mechanisms like rolling element bearing. So, the natural frequency of geared shaft and the gear mesh frequency may have accompanying the side bands. Sometimes side bands themselves may have main indicator of the defective gearbox. So, if there are side bands in the near to the gear mesh frequency, then we can have the fault in the gearbox. So, this is a typical spectrum for a healthy pinion with indication of the mesh frequency and its sideband at no load condition. So, you can able to see that there is a mesh frequency for a typical gear and this kind of sideband. So, only one side is there, but if severity of the fault is more, then we can have sidebands on other side of this main particular frequency. And this mesh frequency will be there always, but if there is fault, then the amplitude of this will increase. This is a typical time domain signal. Generally, time domain signal is very difficult to analyze, but in this particular case, the signal in time domain for one chipped tooth pinion. So, one tooth has been chipped or removed, and in that obviously we will be having impact. So, whenever there will be that particular teeth will appear during the meshing, there will be impulse, and you can able to see there are impulses which are there, that is indicating that the one tooth has been chipped off, and this could be indication of which one tooth has been chipped. We can have a baseline signal, and we can able to compare with that. These impulses may not be present in a healthy gear. So, in the today's lecture, we have seen various kind of fault, and without going too much into the mathematics, we directly try to see these kind of faults, how they can be detected, especially through vibration signatures in frequency domain. We took up various kind of fault like unbalanced, bowed shaft, bent shaft, even the rubs, gears, bearings, and we have seen that each of these machine elements or this kind of faults, they have some unique frequency which they give, which they reflect in the vibration signal. And as a maintenance engineer, obviously we need to look into these frequency continuously, and if they appear suddenly, then we should able to pinpoint where the fault is appearing or where the fault is starting to grow before the failure of the whole machinery may take place. In the subsequent lecture, now we will be extending the similar concept of the condition monitoring, but we will be giving more broader view of the condition based condition monitoring, in which we will be looking into the various techniques which are available at present, and what are the research people are doing on that particular topic. So, just we will try to brief them in the next lecture.